development is not taking place in time. From the maintenance point of view, the maintenance cycles has become longer, but the performance is expected to be the same. The maintenance cycle is long because the regulatory requirements and demand from the consumers. We are not getting any longer outage times. Permit to manage work for maintenance is a bit difficult to get nowadays for the extra high voltage system. So outage time is less. So because of that, less maintenance is being carried out. Again, the assets have become susceptible to failure. Finally, the regulations, they're also demanding a lot from the utility. They're demanding higher return on investments. Not only that, the quality of supply needs to be improved nowadays. There's a regulatory requirement for providing quality supply. So these are the trends and difficulties faced by the power utility. Now, let us look at the need of the hour. Failure. Avoiding failure is the main thing now. If there is a failure, it causes significant reputation damage because of unplanned downtime and faults. We are well aware of those things in papers, newspapers, in magazines. Everybody will immediately be blamed for any failure of the system. In the reliability, there in that portion also, highest reliability is demanded. Availability is also has to be the maximum. That's even a regulatory requirement that the system should be about 98% availability should be there. So that's another big headache, maintaining the availability with this aging assets. So manually managing the assets is a big task now because of these things. Again, unreliable power supply will drive away the industry and limiting the economic growth. That's another factor. Then it again affects the productivity, and often the plant and infra operation requirements are also affected. Another thing is health, safety, and environment, where we need to provide a safe working environment because of the complexity of the grid. Now you require more innovative technology and automation to ensure safe working environment. For improving the health and safety, we need to go in for the latest maintenance strategies like predictive or preventive predictive maintenance. It's also called prescriptive maintenance technologies, where we have to adopt innovative technologies. Need for the asset management. Let's look at why it is required. Effective asset management often helps in overcoming the challenges of harnessing the full potential of the assets. Because manually, if the asset management is not proper, the utilization of the assets will not be fully there. Then again, quality asset data on a GIS platform, Geographic Information System platform, will provide information on details and location of assets graphically. Their condition and performance level, you will have more very good situational awareness about this. There are relative importance with respect to the grid and the geographic location. Sometimes the assets that are in high demand area or in cities may be of more importance than those in the rural areas. And they will provide best return on investments also through analytical methods. What does asset management means? Basically managing life cycle of an asset. Actually, it is a cradle to grave concept for optimizing the cost, risk, and performance over the whole life of the asset. It's important in cradle to grave concept. It consists of asset planning and installation management, asset data management and tracking, asset operations management, asset health management, and finally asset end of life management. That is from asset acquisition to its end. The whole cycle is being managed by the asset management system. Then planning and investments, what does it do? It decides when new assets are needed through planning, long-term planning, short-term planning, and mid-term planning will be there for determining what sort of assets should be there, how much it should be there, like that. What assets and configuration are appropriate and economical, what form this asset should take. These are determined in the asset planning methodology. And in operations and maintenance option, that's the second methodology. Asset performance package is there, wherein it ensures asset remains fit for purpose over the operation life through proper maintenance techniques. Operating maintenance and refrigeration plans will be there, and its condition will be assessed over time. And when it reaches the normal end of life, it can be either given life extension or refurbishment as appropriate, or it can be repaired at the end of the life. At the end of the life, it will be evaluated whether and when the asset should reach the end of life, depending upon the assessed conditions. Then, whether the asset should be there or not, whether you need a real new asset there, then maintenance cost should be considered, and the new configuration and reinvestment should be planned. So these are the life cycle management in brief. ISO 55000 000 is a standard for asset management, which describes all these sectors of cycles of asset management. We will not go deep into this. Anybody can refer to ISO 55000 for details on asset management. It lays out the principles and structure for the system structure for asset management. In every asset's life, there's a bottom curve. During the initial phases, that is, here it is depicted by A to B, is the establishment phase where the asset is acquired. In that phase, the failure rate of the asset will be high. Like it is similar to people. During the infant stage, there can be failure, there can be death also. Likewise, that in the A to B, there is high failure due to, it can be due to management issues, it can be due to operational problems or misuse, or whatever it may be. That phase will be very high. And after that, there will be low failure rate line where it is stabilized and the asset is in operation, wherein proper maintenance will ensure that it reaches its life without any problem, end of life without any problem. And at the end of life, you can either do refurbishment or strengthen it to extend its life. If we don't do that, then it will have its natural death. So this is the bathtub curve which depicts the life of an asset from its establishment to its end of stage. Now let us look at what is the traditional asset management that has been taking place. Till recently, there was not much of a tracking of assets or recording of assets that is available with the utilities. It was there, manually entered in local registers or in Excel sheets, often inaccurate and non-updated, because there was no lock built into it so that it gets automatically updated. It was very difficult to have a common access to this information. Asset tracking was not told there. You don't know what was the status of this asset previously, where it has been, whether it has got any maintenance history. Nothing was known. It was also very difficult to identify ghost or zombie assets. Ghost or zombie assets are those assets which were there but now not in service. Either it would have been reached its end of life, it has been transferred to some other site, or you might have dismantled it. But these might be still there in the registers. And spare management was almost nil. There was no transaction repair or maintenance history, and life cycle management asset replacement strategy was not at all there. So this was the traditional method of doing asset management. Now, because of this, why we need need for innovative technology? Why do we need that? See, the ultimate object of any traditional or smart asset management is to help or reduce, minimize, or optimize the asset life cycle cost across all phases of its life, from asset investment planning to operation maintenance through decommissioning, disposal, replacement. So that's the need for innovative technology, because if you are going through the traditional method, achieving this will be next to impossible. That is the experience of all utilities. So that's why we are going for innovative technologies now. Then why now this hype about this? Because sensors, IoT sensors has been very cheap. IED cost, intelligent electronic devices cost, has come down. Earlier it was very costly. Nowadays it is almost comparable with other technologies. And due to the recent advancements in protection relay hardware and technologies, it is possible to utilize relays in performing asset management apart from protection and control. So there's another advantage having an IED. Then the bandwidth, communication bandwidth has become cheaper, and IPv6 has come into place so that you can have number of sensors, addresses, sensors can be there without any restrictions. And again, cheaper storage and processing has come into picture with the cloud storage, cloud processing, and all stuff. Then again, better and affordable communication technologies come into picture. A lot of wireless technology is now available, stable, cheap. Again, there is another technology, unmanned aerial vehicles, drones based technology is there, big data analytics is there, artificial intelligence has matured, cloud technology is there. So all this has contributed into going in for innovative technology now. This is there in all sectors basically. The smart grid has contributed to that. What's the importance of innovative asset management solutions? It minimizes the need for on-site supervision and intervention by technicians. That's a big advantage. You can have remote diagnosis and assistance to the local people. It reduces the maintenance and operational cost. It improves the reliability and efficiency also. Because of the minimization of technicians and the asset monitoring, enhanced safety and security is also there. Then increased flexibility and scalability is also there, which all improves the situational awareness. Let's look how it is being implemented. In the field, we have the field equipment integrated with the sensors here. We may have additional online condition monitoring units in the field at the process level. Then you have a communication network, fiber, RS485. It transmits the real-time data to your higher-end systems where the artificial intelligence, machine learning, or big data analytics will be there. It is a data-driven expert systems will be there, along with digital twins maybe. I mean, this is the typical structure of a smart asset management system. Now, asset management in electric power systems can be broadly classified into four main categories based on the possible time scales. It can be real-time, short-term, mid-term, and long-term. Real-time asset management mainly covers the key power system resiliency principles and deals with the unexpected outages. So there is basically operational thing. Short-term AM is for maximizing the return on asset investments through optimized usage of assets. Now, optimized maintenance schedule will fall within the mid-term AM. And the long-term AM is basically investment planning of grid expansion. Okay, these are four types of asset management techniques. Okay. Now, the smart asset management structure is like this now. Just to give a brief of how it will look like. You have external IoT platform connected assets connected to this your expert system, asset management system, which measures asset condition and performance data, geolocation data, and weather data will be transferred to the system. Then the maintenance inspection activities by the maintenance team will also be given to the system. Then inside the system, you have three modules: asset investment planning module, asset performance management module, and computer maintenance management system. Computerized maintenance management system is basically asset maintenance management system module. So these are all will be based on AI and ML analytics, artificial intelligence and machine learning analytics. And it will be communicating to the ERP system of the utility also. So this is the basic arrangement of an asset management, smart asset management system. Now let's look what are the expectations of a smart AMS. Mainly, it should be capable of collating and storing the online condition data from various sources. It should be automatic or manual integration of condition monitoring data from a range of assets, and that too from a range of sources, including IEDs, sensors, smart meters, and SCADA systems. There should be common reporting and analytical capability for consolidating the reports, including static data analysis as per utility requirements, like asset condition ranking, age profiling. The asset, you can profile the age of the assets. Manufacturing date-wise profiling, make-wise profiling, maintenance statistics, estimate remaining life, and those things can be reported. And again, you can have condition monitoring and data analysis like to support like a probability of failure, health indices, including the trending and what if modeling, what will happen, like that sort of modeling can also be done. There should be able to easily view a range of asset-related information traversing the asset hierarchy and via search facility. And there should be configuration management alarms indicating deteriorated or impaired assets. Whenever the condition monitoring analytics indicate an asset is nearing, its end or is impairing its function, that should be alarmed. And there should be an algorithm for developing the maintenance concepts based on the condition monitoring data. Then again, development analytics and health indices for asset condition assessment, remaining life forecasting, and asset management prioritization also should be there. Now let us look at the best management practices. You have to choose the technology carefully, because without the appropriate technology, in asset management technique can fail. You have to choose the right hardware and software. It should be economically viable. You have to remove all the ghost and zombie assets from your collected data. Then you have to analyze the asset performance in a periodic manner. You have to track the asset depreciation, proactively carry out asset maintenance, and you have to comply with the statutory and regulatory requirements. This is the best asset management practice that is being invoked. Now, the innovative practice is like that. You have to leverage the digital transformation to modernize how one manages assets for smart investment planning and more efficient maintenance operations. There should be a holistic and integrated approach encompassing industrial IoT, Internet of Things, collaborative environment, and cloud-based analytics. Predictive, prescriptive asset analytics maintenance and decision support platform enables our personnel to make smarter business decisions while reducing maintenance costs by 50%. Recent surveys shown that going for predictive analytics brings down the maintenance cost by around 30 to 50%. That's a huge advantage. Now, this is a digital utility asset management model, wherein it specifies various activities for creating an asset management model. First of all, create is there, where you have to build up sensors, intelligent electronic devices, and advanced meters. You have to plan for these things. You have to this is for converting the physical media to the digital one, your signals to the digital one. Then you have to have a good communication network with the routers, remote terminal units, hubs, and switches. Then you have to integrate these things to the cloud server. Data protocols and standards has to be finalized. Then you have to analyze the data for different analytical tools and high performance computing. Then once you have analyzed and run the analytics, you have to bring it out. The results you have to bring it out to visualize in the dashboards. It can be dashboards, it can be wearables, mobility solutions, or digital twins for analysis purpose. Then you can augment it through artificial intelligence, cognitive, such as machine learning, deep learning, etc. You can do further analytics on those things. Then you can have automated things like robot, drones, unmanned vehicles. An example is, suppose you have done analytics on a PV, and the system, once the system determines that there is an issue with the PV panels, it will send a drone out to take a picture of the panel and send it to the service personnel along with the picture of a good panel to determine how much damage has taken place, to cross check. Then it can do, it can go in for a purchase from a pre-listed vendors that's given by the system itself. And this sort of automations can be done. Then again, it can be left to the human to take a decision, and human decision making. And finally, you have to see the financial and the operational KPIs, key performance indicators. Then you have to report the data in spreadsheets and other forms. So this is the basic digital utility asset management model. Again, in between, you have to build up the cyber security also. This is a big headache in all digital models, where cyber security has to be there. And the implementation challenges. Lack of data integration and standardization. Between the devices, there is no standardized protocols now available. So even data integration is a big difficult. There are numerous solutions available with the minimum integration. Most of the systems cannot be integrated together. That difficulty is still there. That has to be standardized. In substation automation, 618 has come into picture, where all the communication protocols, devices has been standardized. Communication with devices has been standardized. IEDs has been standardized. But still, the communication between sensors, between the software systems is still identity. That is something has to be done about that. Then there's lack of resources, including skilled personal funding. The technology has come up like anything, that we don't have resource persons like in IoT, in cloud computing, in big data analytics, in AI. There's lack of person for this, and that's a big problem faced by the utilities. Then another important thing is resistance to change and adoption of new technologies. People are always very much they rebel against these things. They change. It affects their career prospects. It affects future employment. So there's a huge resistance to change and adoption of new technologies. Then the complexity of asset management systems and processes. Because if you want to adopt innovative technologies, you have to digitize the system. You have to digitize the process level as well as the station level. So digitalization means incorporating sensors in the existing assets. It's a big problem. It's very complex. You have to find solutions for that. Then there's difficulty in quantifying the benefits of APM. If you want to put up this proposal to higher management or even to regulator for approval, you need to have financial viability, and there should be a viability analysis. And it's very difficult to quantify the benefits of APM, asset performance management systems. And finally, there is cybersecurity. It's another big headache, which is now being addressed. Okay. Now let us look at the asset maintenance strategies. Now, there are 5 types. One is run to failure, which has been there from way long back. It's actually a reactive maintenance wherein you react when the system fails. You attend to the asset only when it fails. That is run to failure. It's a reactive type of management. Then there's time-based management, where a scheduled maintenance based on the schedule given by the OEM or as required. This is basically a time-bound one, where you do annual maintenance, quarterly maintenance, monthly maintenance like this. That will be done whether the equipment is healthy or not. I mean, it doesn't matter. Even if it is healthy, you'll do the maintenance. That's time-based maintenance. Then usage-based maintenance, wherein you look at the usage of your equipment, and if it is highly used, then you go in for maintenance. That's usage-based maintenance system. Then there is the new ones, condition-based and predictive maintenance. That's the new maintenance technologies that's comparatively new, you can say. Condition-based means you look into the condition of the equipment based on the monitoring parameters you accrue through the sensors. Then you do the analytics of the accurate data and see what is the conditional system. If it requires some maintenance activity or not, then you do the maintenance. Predictive means you collect all this data, you go for what do you call it? Analytical methods. You use analytical methods like AI and ML for predicting the condition, what will be its conditions, say such and such date. So it may require your attention, or it may not. You can postpone the maintenance by looking at it. Some predictive algorithms can even give advanced warnings. Like say 5 years down the line, this will be the condition of the equipment. So these things are there. Basically, PDM, predictive maintenance, is an advanced level of condition-based maintenance. CBM consists of anticipating a maintenance activity based on evidence of degradation and deviation from the normal behavior of the asset. It looks at the normal behavior, it compares an asset's value with some other normal value and see whether any degradation has taken place or not. If degradation is there, then it will say, it will flag it, and it will say that there is some anomaly. Okay. Now, PDM is, it predicts the remaining useful lifetime of component. That's the difference between CBM and PDM. CBM doesn't predict, PDM predicts the remaining useful lifetime of the component. Okay. Basically, the traditional CBM is enhanced by ML algorithms and digitally tuned to diagnose and acquire detail status and to predict. Okay. So again, this we had discussed earlier. Every new asset has a service life, which ends here if only reactive maintenance is done. Because reactive maintenance, what will do, it will gradually deteriorate the equipment. So finally, it will reach its end of life. But if you go in for proactive maintenance, you can improve its life again to some other, extend its life to some other stage. And again, you can do a proactive maintenance and again extend its life further. So that is the beauty of having a proactive maintenance. Okay. Now, predictive analytics is a process of using statistical. I will talk more about predictive analytics now. Predictive analytics is a process of using statistical and data mining techniques to analyze historic and current data sets, and will create rules and predictive models, and using which it will predict the future events. Now, what's the advantage of that? The shift to predictive maintenance improves the crew utilization. You have a crew, you can use it more effectively. You don't have to run these crews to do routine maintenance work. You can utilize wherever it is required only. You can minimize, you can skin down your, you can bring down your crew strength. You can slim it down. And then you can avoid unexpected outages, improving the customer satisfaction, reliability. And you can also, because of this predictive maintenance, you very well know when the maintenance has to be taken place, so that you can communicate to the customer that such and such outage will be there on such and such day. I mean, that will be bringing more customer satisfaction. Then again, safety and compliance. Proactively address potential safety risks and compliance issues by collating and analyzing data from multiple sources. Because predictive maintenance is what online data monitoring facility where it collects data from different sources, amperage, internal to the assets, external to the assets. I mean, all this data will be compiled together, and using predictive algorithms to say you can address the safety issues and risk factors. Then finally, because of doing predictive maintenance in a timely manner, you can reduce the total cost of ownership. Okay, because you can actually factor in the health of the equipment in maintenance planning, so that you can reduce the maintenance period, maintenance duration, and maintenance activities, so that you reduce the cost of ownership of that particular asset. Then this is a structure of a typical predictive analytics environment, wherein you have both external systems coming into play and internal systems. External systems means the predictive analytic logic will take information from SCADA, the historians, and online monitoring systems, weather service, etc. And again, it will have real-time information from other sources, weather data, prediction, and using those things, and it will have weather predictions also. Then you will have your rules and repositories inside, rules repository inside. Then you have analytical engines. Then it will, based on these things, it will schedule jobs, maintenance jobs. I mean, it will create KPIs, and this information will be given to enterprise asset management system as well as the GIS service for displaying the GIS database or dashboards. Then finally, you have the HMIs, human machine interface, where we have the operating dashboard, predictive notifications, asset model, and predictive route setup. This will be given either to desktop or mobile applications. So this is the basic structure of a predictive analytics environment. Now, maintenance strategy for substation. This is a relatively new one. Usually nowadays, the maintenance strategy is based on reliability-centered maintenance model, RCM. This, what you do is, even if an asset is flagged for maintenance, the system will look into how critical this asset is for a network. So how critical it is for the reliability of a network. Based on that, it will prioritize the maintenance activities. So that is called reliability-centered maintenance. It requires a lot of information, a lot of knowledge to identify the critical equipment that is very much necessary for a reliable power system. So basically, a substation plan failure modes relate to the inherent design characteristics. Any equipment, it will relate to the inherent design characteristics, surrounding environment, the load applied onto it, and the stress and duty cycle. Any equipment, this is the typical nature of failure of any equipment. Now, the philosophy of maintenance is like this: non-invasive local and remote performance monitoring and condition assessment through condition monitoring and testing. You will do an online condition monitoring and online testing. And you will do invasive maintenance only if it is absolutely necessary and there is no practical alternative. So it brings down the outage time like anything. Continuous performance monitoring, routine scheduled maintenance, visual inspection, condition monitoring, and testing are all used to detect deterioration of the condition or degradation of performance substation plant. That will, if allowed to continue, result in asset failure sometime in the near future. This is a technique. So RCM analysis to be undertaken by review teams. This is the most important one. Review teams of technical experts and field personnel with a reliable knowledge of the network assets being analyzed. So here is where the innovation can come into the picture. Here you can go in for AI-based expert systems. That's happening now. You have expert systems where it can give out, you can identify the critical assets based on network topology and the historical performance operation data. So now let us look at the modern condition monitoring techniques. This is basically the theory part which I covered to make you understand what asset management is, what are new techniques being used there, and those sort of things. Now we look into some of the practical aspects of the system. You can have either offline mode or online mode for condition monitoring. Offline mode means you do a portable analytic, you have portable analytic kits which you take to the equipments and do the analytics. Okay, you measure the things, you bring it to your server, upload this data to the server, and do the offline models. That is there. That's always there for normal routine maintenance. But again, you can go for online monitoring, wherein all these devices become smart. Your GIS, your AES, your smart cables, your transformers, your generating machines, everything can become smart. It will be Wi-Fi connected basically, where you have sensors integrated to that with the Wi-Fi connectivity. So what are the online monitoring techniques? There are different techniques. I'll list some of the techniques here. One is vibration monitoring. Then the oil analysis, DJ analysis, tan delta, things can be done. Then infrared thermography is there. Ultrasonic testing is there. Partial discharge monitoring will be there. And finally, the real-time monitoring of all the parameters. So these are the different modern condition monitoring techniques available. A few of them, I have not listed all of them, but still the most important ones is there. Now, let us look at the smart asset health management process. The condition and predictive approach. Its main goals are to reduce catastrophic failures, reduce unplanned outages, optimize maintenance, increasing the productivity, and managing the asset life cycle. Now, the benefits, it reduces the maintenance cost, downtime cost, and repair costs. The benefits is reduced failure rate, better maintenance cycle, replacement plans are optimized, asset lifetime is improved, and productivity is increased, which all brings up a savings in O&M costs, capex, and outages. Approaches like this, you capture the data through sensor technologies, diagnose those data using algorithms, inform the asset management, and get the services of the experts to act upon. Let us see how it is being done. Monitored variable with an unexpected trend discovered. See, this equipment is being monitored, and that variable shows an unexpected trend, and the system captures an unexpected trend on the data. So what does it do? The field service gets alert on asset health changes by the monitoring and diagnostic system. Then the service expert will evaluate the alert, analyzing the health condition of the asset according to the application, historical data, and field experience. So this is the diagnostic stage. Then what it will do? It will inform the service expert. The service expert will call the field officer, explaining the possible risk and the suggested mitigation actions. Then the service person will act. If a check or maintenance activity on site has been agreed, the field person will act on the site. Finally, what happens? Everybody is happy because you have mitigated a failure before it happens. So this is the way a smart asset health management will act. This is the process flow, basically. This is a smart health monitor for an MV switch here, where the set of binary inputs. In every IED, there is a binary input and binary outputs are there. The binary input will monitor circuit breaker operations and timings, as well as other warnings like SSX low pressure. Okay, these signals will be available in the low voltage compartment, and the contact wear indication shall be obtained. Every breaker will have a fixed and moving contact, and where if the contact gets wear out, the breaker will fail. If it gets worn out, the breaker will fail. So you have to monitor the condition of the contacts, which will give you an indication of remaining life of the breaker. So through Hall effect current sensors, clamped circuits of the current transformer, to monitor the fault current to be measured, and by modeling the breaker, you will see how much contact has deteriorated, worn out. Again, the spring charging motor current will be monitored to see whether there is any mechanical or deterioration in the system. If there is mechanical deterioration, the spring charging motor will take more time, more current for charging the breaker. Again, the asset will be identified through RFID technologies, or there can be RFID, there can be QR code. I mean, those things can be used for identifying the asset. That will information fed to the system. Then these are the schematic diagram of how the breaker is being monitored. Binary inputs monitors operating centrally, the trip coil, the closing coil, operating mechanism, and the closing or open signal to breaker. Current sensors will detect the current and spring charging current, breaker current as well as spring charging current. RFID will give the breaker information. Then auxiliary voltage will be measured. Infrared sensors will measure the temperature inside the cubicle. Then the configuration will give the equipment data parameters. So all this will be diagnostic. The algorithm will diagnose these things, and analytics will be run, and there will be indication. Just simple indication. The output will be very simple: red or green. Red indicates there is some problem. Green indicates that okay, the system is healthy. Okay. So this is the simple method of smart asset health management process. It's already given. And we'll go in for. There's another thing is there also there, hotspot temperature monitoring. Every breaker compartment, every breaker will have joints, and these joints are closely monitored for in rising temperature. If any thermal runaway is there, then the breaker can, there can be failure of switch gear for the equipment. So these will be scanned, and the hotspot will be determined by checking against the ambient temperature. To look for temperature difference between various points also, and it will generate a warning if there is any deviation from the normal. So the sensors are mounted in the MB switch gear. You have sensors in the cable compartment, main compartments, busbar compartment, and infrared hotspot temperature in the joints will be there. Okay. Again, you have dashboards listing out all the statuses of various equipments in a single platform. Then we have this is different shots of the dashboard. You have equipment information here, overall health condition here. Then it will estimate the what main estimations and calculations, like what's the maximum, minimum, what's the maximum life of this equipment. I mean, those things can be given here. What is the maximum load it has carried? Those things will be given here. Then again, we use the minimum, maximum, and average values with the proper color coding. List of latest events, switching operations, fault interruptions, and everything will be given here. And the last scheduled maintenance when it was carried out, those things will be listed out here. Now this is for outdoors SFCB monitoring. In outdoor SFCB monitoring, it monitors the interrupted wear. Again, the contact wearing, where indicator will be there. Integrated SFC gas system will be monitored. Circuit breaker mechanical system will be monitored. Electrical control system and auxiliary will also be monitored. The sensor will be mounted in the circuit breaker chamber. This is a typical example of a SFCB monitoring system. Breaker current will be monitored. Total travel will be monitored. Contact velocity, reaction time, coil ionization time, trip count, etc. This is actually a schematic diagram of the system. Then you have the GIS monitoring again. I'm just talking about various monitoring systems available nowadays. Again, here also, all the parameters will be like current, voltage, motor current, trip coil, oil, closing coil currents, switch current, switch disconnector current, switch currents. I mean, those things will be monitored. Then again the hydraulic pressures. If it is hydraulic mechanism, if it is pneumatic, then the temperature, then the pressure, air pressure. If it is spring, then the motor charging currents. Those things will be monitored. Ambient temperature will be monitored. Resistance pressure, humidity will be monitored. Then again, it will display all the currents. Output will be all the values will be displayed in the dashboard, and any abnormality noticed in these measured values will be flagged out also. This is actually a partial discharge measurement system for GIS, where any partial discharge taking place in the GIS compartment will be captured and analyzed and displayed in the smart PDM system. And for power transformers, we have different systems available. There are Buchholz relays, which will carry out gas analysis. The system itself will carry out gas analysis indicate the fault type, which is the latest thing available in the power transformer. We used to have traditional Buchholz relays, but nowadays Buchholz relays has become intelligent by itself, and it gives out the transformer condition. Whenever a tripping happens, it will analyze the gas itself and gives out a trending information on these things. Then the transfer temperature, cooler bank temperature will be monitored, hotspot oil temperature and wine temperature will be monitored. Then the transformer, the DG analysis of the transformer can be carried out. Again, bushings will be monitored, and the total system, the insertion values of the system can be monitored, and these things will be done through the latest technological devices. Now, these are new devices just coming to picture for transformer monitoring. Branch mounted sensors are there. Okay. And these are the measuring points in a transformer where we put the sensors, where is for determining all these parameters. This is a monitoring system provided by BHL, where it will do monitoring, forecasting of the life as well as the loading. It will estimate the future life of transformer to protect as well as control. It's basically 60950 based equipment that you can communicate with the upper SCADA system also. It monitors the cooler banks as well as the tap changer. It will give the residual life estimation based on the loading of the transformer. 60076 is the gating load. It's a gate for loading the transformer, and based on that, it will find out the residual life of the transformer. It's a condition-based maintenance data. Now, online DG is another technology which is being used now. Dissolved gas analysis for transformers. The analytical software will do the once you capture the data, it will do an analysis and it will give a notification also at what sort of fault has taken place, what's the gas content in the oil, and what are the different gases that is there, and those things will be monitored. And it can also combine with additional transformer condition-based monitoring devices like tank pressure, cooling bank current, winding current and temperature, bushing monitor, partial discharge. So these things can all be combined together to give a condition-based assessment of the transformer. So nowadays, systems are not standalone. They can take inputs from other data also, for other systems also, and do the analytics. It's a PD monitoring for transformer. Nowadays, early days we used to have radio influence methods of wideband and narrowband PD detectors, but nowadays we are going for ultrasonic detectors, acoustic detectors, which is more accurate, and it's a very good installation for giving out the condition of the transformers. Because PD is often present well in advance of installation failure. Therefore, monitoring partial discharge will give you a good indication of the defects or deterioration in transformers. This is the PD monitor and PD device, along with the graphical indication of the same thing. This is how a dashboard will look like. This is all futuristic, you can see, because it's very complex. You need a real understanding of the system to analyze these things. And again, you have nowadays we can monitor the cables also. Earlier, it's very difficult to monitor the underground cables, but now with the distributed fiber optic sensing technology, distributed temperature system and distributed acoustic systems, we can monitor the cables, healthiness of the cables continuously. It can be integrated with the other things like intruder, third-party intervention. When somebody digs into the cable route, it can detect it and give an alarm to the operator, to the field staff. Then there's condition monitoring, seismic monitoring also. When there's any seismic event, you can capture it and send an alarm. I mean, these are things that is there in cable monitoring. Now, it's very advanced nowadays. Even in fact, in the VSC HVDC, we have a cable system. In Madakutara, we have a HVDC station where the cable is coming from one sector is having cable, and the whole cable is being monitored remotely. Okay. Now again, for monitoring the insulation of insulation materials, leakage through the materials, that can also be monitored nowadays. You have wireless battery systems available now, sensors available now, which you deploy at the grounded end of the installation. It will monitor the any leakages there and it will give an alarm. So even the insulators in your substation yard or in transmission lines can be easily monitored. Now, these are all monitoring systems. And when you talk about smart asset management, you go in for latest technology solutions also when you procure the assets. This is a new technology for a GIS, which is called Blue GIS. This is available up to 145 kV. SF6 medium is not at all environment friendly. So now people are talking about replacing SF6 with some other thing. It's called, this is a new technology which is given by, many people are doing it. This is by Siemens. We are also doing that. So it uses clean air basically. Instead of SF6 it uses SF6 to use clean air. Clean air means it's basically 80% nitrogen and 20% of oxygen, basically. Clean air means 80% nitrogen and 20% oxygen. It's known as clean air. This is given for providing insulation. The interruption takes place in a vacuum chamber. The vacuum technology is used for interruption. Normally, SF6 breakers, SF6 is used in both in interruption media as well as for insulation purpose. But here, insulation is through clean air and the interruption is through a vacuum interrupted technology. So this is available now up to 145 kV, and it is already in service in Norway and Germany. It is the latest in GIS. It's available for CTs also nowadays, and in AS also it's going to come up. I think it's already there. Okay. Another technology is optimization of lines, dynamic line rating, wherein the thermal loading of any line is determined by the design parameters based on ambient temperature, like maximum permissible conductive temperature, wind speed, solar radiation, absorption coefficient, humidity coefficient, ZAG, etc. By measuring all these things, by remotely monitoring all these things, the system can determine what should be the loading of my line at any particular point of time, depending upon the ambient conditions and the sag of the conductor. So that is a real, rapid technology, because it actually spreads out your investment basically. Suppose your line is heavily loaded, it is going to reach its thermal loading. So you may have to plan for new lines, or you may plan for upgrading the line. But once you install DLR, it will give a dynamic, dynamic state. What is the condition? How much loading can take place? Maybe it can be loaded more than thermal rating depending on the ambient condition. So it can defer your investment. So this is a good method of asset management. DLR, dynamic line rating. Actually, we had done a project in Kerala, in DLR at Vadatho, and we found it increases the line rating by around 20 to 30% existing lines. So this is the basic system of dynamic line rating. You have environment condition monitoring done here in the lines, the line sensors, and again there's a communication gateway. It can be 3G or basically GSM network. Then you can have backend communication gateway to DLR analytics engine, which will be cloud-based one, to do analytics of the whole system, and it will give information to SCADA master, SCADA system, saying that this is your current, this can be your current loading. So that will be a big help for the system operator. Then you have the integrated power flow controller. There is Intelligent One. You see at many places there can be unbalanced loading in the lines emanating from a substation to a particular load center. It may be because of impedance mismatch. It can be due to line difference in line length. Several factors can be there. If that happens, you may have to plan for additional lines. Here also you can go in for intelligent power flow controller, which is basically based on static synchronous series compensator technology. Here you can suppose here the issue is this line is getting overloaded. Okay, power is not equally shared across the 3 lines. Now what you can do, you can put a smart valve here, which will push out this power from this line to the other 2 lines. Okay. Likewise, you can improve the loading of the lines. This file is running now. Now the future developments and trends. Basically, nowadays we'll be going for Internet of Things, IoT integration, and edge technology. The edge technology is a new one, basically. Basically, what happens is it will take the processing power to the field devices. It will make the field devices more intelligent so that it can have its own processing power and algorithms integrated into that. It can take its own decision. It basically a distributed environment so that the decisions will be faster and your server systems will be offloaded. And there will not be any latency in the decisions. So that technology is also coming up fast. Then there's artificial intelligence and machine learning applications for making and for doing support decision making and all those stuff. Then there's another thing: augmented reality, virtual reality, wearables, and computer vision. This is a very new technology. This is really good in maintenance management, where you can have a wearable with the AI and AR, where you can send the data. Suppose you have a mobile device, you can send the data. You can capture if you are going to the field, you can capture the equipment assets. You can show, you can the data of you can capture the asset through the mobile camera, send the data to the server, and the server, along with some markers, will also be sent. It will scan its database for equipment for information related to this particular equipment. It will draw out all the informations like maintenance informations, its test values, whatever test you have done, those values, and the results interpreted by the system. I mean, everything will be pulled out and to be shown on the wearable worn by the field operator. So he can take instance decisions, and the server can also direct what to do with the anomaly noted in the field equipment. I mean, those things can be done. I mean, that's a new technology evolving. Already there are pilots running in this thing. And now the second thing is digital twins. That's also another technology where you don't have to do any analysis on the real equipment. You can have a software model of the equipment, of your actual equipment. You can have a software model of your actual equipment and do all the analysis on that, and then produce a result, comparable result, and then implement it in the product. So those are the things: digital twins and simulation-based asset management. Then there's big data analytics, because the data that is coming from server is very huge. Trillions of bytes of data is there. Normal systems cannot analyze that. So you have to go in for big data analytics and advanced algorithms. Then there is ground zero analytics. That is basically based on augmented reality and VR. Okay, those are the new technologies that is coming in. And during a recent survey regarding this, is a 2021 survey, basically, most of the utility people, I mean, they were asked which is the most important technology that is required now for digitization of the assets, and the response was AI, machine learning, is the most important. 55% of the respondents saying that it is the most important thing. Then cloud-based technology and IoT came into the picture. Then again, augmented reality and drones. Okay, these drones are a relatively new technology, but it's very popular now. If time permits, we'll have a session. We will have a small reel on that also. You'll see a small reel on that also. Again, I'm talking about this thing: improved situational awareness through AR technology. This AR and VR data visualization gives an immersive experience for the field operator. So now the better telecom bandwidths and powerful mobile cameras, along with AR techniques, have made it possible now to view, point, detect, and transmit and identify objects, coordinates, and other information to the backend systems for further processing. So during the image analytics, it can leverage all these things together and bring back to the field person, the real-time data about this particular equipment. Basically, the convergence of the three technologies like visualization technology, image analytics, and AR technology. So this is called ground zero analytics. So this is a really new technology that is coming up now. Then you have continuous remote monitoring. Because of big data, because now big data can be handled easily, you can have continuous remote monitoring, 25/7 continuous remote monitoring to optimize the day-to-day operations with smart alarming and proactive equipment failure warnings. IoT, we already talked about IoT. It is a foundation of any smart AM system. Okay, it's a network that enables smart things to be connected through internet, basically. I think everybody will be knowing about that. Basically, it is the intermediary platform between the hardware and the application. It's a middleware application. IoT is a middleware application which connects the hardware to the digital cloud. Now it brings some real-time condition data, self-monitoring, remote access, improved remote operation, better data analysis, and increased data and increased accuracy in determination of end of service life, reduced exposure of workers to safety risks. This is the advantages of IoT. Now the risks with IoT is it compromises cybersecurity because you have a lot of open bandwidth available network there. Then the record skills needs to change it in order to identify with this new technology. Now the most important thing is loss of rapid intervention skills because people lose their skills. Everywhere where automation has taken place, we've seen that the people lose the actual skills to intervene when it is necessary. They're more dependent on software and the systems. They won't be able to take decisions their own. That's the difficulty that we have seen in KSEB also. Wherever we have automated the system, the operator is lacking all these things. So lack of rapid intervention skills and technical knowledge is the biggest problem. Then risk associated with loss of communication. If there is any loss of communication, then the whole system will collapse. Then again, next thing is particular to India as well as Kerala, shorter expected service life of devices under tropical climate conditions. That's another problem being faced. We have to make it more rugged. The emerging trends, optical communications, integrated monitoring, all the thing, electrical, visual monitoring systems, firefighting systems, weather, fuel tank, everything will be monitored, will be linked to one particular system. Then we should be having low power intelligence sensors with edge processing, which I already talked about. There will be redundancy in all the sensors, cybersecurity, interoperability will be there, real-time situation awareness will be there, data historian will be there, then UAV-based intelligence systems will be there, like drone-based intelligence systems will be there. It's already there. Many utilities are using it. Then there could be condition monitoring and ambient monitoring, access control and virtual fencing will be there, digital twins, point-and-wave switching, cloud-based storage analytics, wide area monitoring, dynamic lighting. Those things are the new things that may come up in asset management solutions. Again, this is a new one. This offered by Siemens. Those fellows. This is predictive analytics. Nowadays, what is happening is predictive analytics. Tomorrow, what is going to have is prognostic, wherein you will have the life of the asset predicted for the next few years down the line. Okay, that's a very important good thing. Because of the power of the analytics and the data that you are capturing from the system, you can predict, you can forecast the life of the equipment, what it is going to be in the next few years down the line, if the load pattern and the other ambient conditions is according to this. I mean, it uses fuzzy logic. Several things will be used there for predicting these things. Basically, it gives a when and what if scenario by helping companies to better understand the trade-offs and impacts of different possible scenarios. Now the technology what is seen is that the technology accurately predicts 99% of equipment malfunctions with a time horizon as much as 5 years. That's the beauty of the thing. Okay. Now, if you know when the asset is going to fail, you can properly schedule its maintenance. You can even prepone or postpone your new asset coming into picture. Those things can be done. That's really beneficial for the utility. Now, and so do we have time? Because there's something related to innovation with UAV. So some reels regarding what is the use of UAV nowadays in line maintenance and all stuff, AI-based line maintenance system. For time, we will cover this also. Otherwise, Anissa, are you there? Hello.
Hello, sir. Hello, sir. I'm Aksharas. I'm the student representative. Yeah. Sir, please continue, sir. We do have time.
Okay, fine. Then I'll move along with this also. This is innovation with the UAV, basically. Because we have now unmanned aerial vehicles in operation. It's already in operation border security forces, in agriculture sector, in railways, and several places. Nowadays, these are being used in utility sector also. PGCL is having a host of drones for maintenance purpose, for inspection of lines. And UAV along with AI is giving a lot of advantage in preventive maintenance. Let's have a look at it now. The need, why it is required. This transmission lines need to be inspected on a regular basis for reliable and secure supply. Minimum vegetation clearances to be maintained. They go to different threshold. Inspection status, cracks and damage has to be done. weak, damaged, missing in hardware, and bird nest has to be removed. Hotspots or contact damage has to be detected. These are all the things necessary for during a line investigation, line inspection. Now, present practice is through manual methods, foot patrol, drive-by, binocular vision, climbing towers, etc. It is low accuracy, safety issues are there, high manpower demand, slow inspection, blind spots will be always there, and there is of course terrain difficulties. So these are the problems faced by the crew nowadays. The drivers force these technologies like difficult terrains, high risk safety concerns, inaccuracy in detection of abnormalities, time consuming, delayed maintenance, longer outages, improper records, etc. These are the things which draw in people to go in for UAV. Again, there are developments in UAVs. It is not like the earlier days. Now there are huge development in UAVs and sensors, AI and ANN. Now we have higher payload capacities and longer flying time. Earlier, the flying time of UAVs was very limited. Now we can have 45 minutes to 1 hour flying time is there with the full load. Newer configurations are there. Now high resolution cameras are there. 4K cameras are there with a 30x optical zoom. LiDARs are there. IR detectors for thermal images are there. And the AI proficiency has also gone up. Now, as I told you, there is widespread use of UVs in various fields: solar PV array inspection, pipeline, civil structure, management of traffic, crowd vegetation, crowd management of traffic, and crowd vegetation assessment, forest fire detection, crop assessment, coal pile, volume inventory, disaster management, border monitoring, firefighting, etc. Only utility is missing in this. The key takeaways are we can have an expert system for automatic detection of predefined abnormalities during inspection of the power line using UAV. That is the most important thing. Photogrammetry can be applied, vision-based photogrammetry for detecting anomalies in the line, for calculating the vegetation clearance, etc. On-the-fly real-time assessment of corridor clearances, detection of corridor encroachments by vegetation or by people or buildings, detection of abnormalities in insulators, hardware, conductor, etc. Hotspot detection using thermal image sensors. Deep learning-based algorithm can be used for detecting anomalies and predicting the system healthiness. And quantity, the inspection quantities can be increased because normally UAV inspections are not at all time consuming. It's very fast. So you can have number of quantity of inspections. Okay. And they can be deployed very rapidly. Results are available quickly. It's not cost like a traditional aircraft. Can fly under cloud cover. Can reduce the risk to workforce. And you can access hard to reach areas. It can be actually geofenced. The drone will move along the line if it is given geo coordinates. Ideal for surveying and enable rapid asset inspection. This is the system configuration. There will be a bird, there will be a drone, then there will be visual camera with the 30x 4K visual camera, 30x zoom. Then there will be photogrammetry camera, then with thermal image camera, LiDAR, ground control station, and computing platform. These are the basic configuration of a UAS system. And drones have an aerial, they can have 4K resolution image, thermal inspection, zoom capabilities, 3D modeling, etc. can be done. Based on the LiDAR information, you can do a 3D mapping of the whole right of way, whole route of the line. You can easily visualize the clearances, the vegetations, everything can be visualized when you do a 3D mapping. Transmission line corridor inspection can be done. Substation static inspections can be done. Infrared thermal inspection of the whole assets can be done. And PV plants can be, they can use for model inspection of the PV plants. And there's 30 to 50% cost and time savings when drone is used. Okay, safety person is there, and thermal image camera will detect all the failures also. Move forward. There are various applications of various other punctured cracked insulators can be identified, flashed discs can be identified, contaminated insulators can be identified, corroded pins or connectors can be identified, damaged, loose or missing hardware can be identified, damaged dampers, water pins missing, miscellaneous insulators, bird nest, vegetation encroachment. I mean, these things can all be identified through AI, logic, algorithms. Obstructions can be removed, identified or removed. Okay. It's a few reels on that. I'll show you results. This is a short of failure of porcelain body just detected by the UAV. Damaged conductor is also there. So damaged conductor. Then there is a disk failure. Some disks are missing. These things can be identified by the UAV inspection. Again, corroded clamps, corrosion can be detected very easily. See, damages to the insulator can be detected very fast. Again, bird's nest can be detected. Actually, there is no manual intervention required. The AI algorithm will detect all these things. Okay, once you train the system, it will detect all these things. Images. Wherever the hotspots are there, these things hotspots will be identified. So that is another important thing. Then vegetation detection can be there. The clearance report can be generated based on the calculation methods. Like you can really, using the photogrammetric pictures, you can calculate the vegetation clearance and give a report. This is substation inspection samples, where you can inspect the assets in the substation and find out any anomalies there. And this is an integrated system for detecting the PV plants, anomalies in PV plants. See here the anomaly is detected in the PV panel, some anomalies are there. It's basically a pattern recognition algorithm will be run for identifying the defects and pointing it out. So let us just look at some shots here. This is one of the videos. This is another video. This is another new one which used for line patrolling basically. Okay, actually, we have done a similar pilot in Kerala also, KSEB also. We had procured 2 drones with thermal image cameras and photogrammetric cameras with visual camera. And that pilot we did it, and it was successful, but it is still not implemented in KSEB. Okay, to conclude, asset management techniques has come a long way. New technologies are available and evolving. We need to learn to trust and use it. That's the most important thing. We turn data to information to further to knowledge. Now we also should be searching continuously for innovative best practices to adopt for asset management, keeping in mind the best value investors we have available. Okay. So this sums up my presentation. This is caught by Mark Twain. He says you should innovate. This is the mandatory thing for taking innovative items, innovative ideas. Okay, thank you. So any questions is there? You can ask me now.
Thank you so much, Biju. It was excellent. Presentation was excellent, Manu. Very good. Thank you.
Thank you. Thank you, sir. Any questions?
Sir, we have received one question in the chat box. And before that, those who joined the meeting using the secondary link, can you please post the questions in the chat box? And those in the primary link, you can either post it in the chat box or unmute yourself and ask. So the question which we received is, how do you see emerging technologies like artificial intelligence and machine learning impacting the field of asset management?
This is what I covered in the presentation, I think, because AI and ML is going to be the byword, I mean, the next thing for us management. Because without that, nothing can take place. Because the quantum of data and the number of sensor points that you have to monitor, visualize, and run diagnosis is too much for normal algorithms. So not only that, if you want to develop expert systems, you have to train an AI algorithm with the historical records, and then you can have a predictive algorithm going up to predict the healthiness system. So AI and ML is, along with other technologies like big data, is going to be the next in line for the asset management, smart asset management. As platform, you can say, it's already there. It's already like that.
I have a small doubt, Biju. What is smart valve? Smart valve you have mentioned, no? What is it actually? And is it a software something related, or that has to be installed physically on the line? Or suppose if 3 parallel paths are there, then smart valve need to be installed in all the parallel paths or in one path. I have doubts, so many doubts.
So basically, it's a hardware software combination. Okay, that is the technology is based on SSSE, our old technology, SSSE only. Subsynchronous convert, other on that technology only. But the thing is, it is highly, what do you call it, optimized for mounting on the lines. Earlier days, SSSE is begun, which has to mount the structure in the substation. Okay, but with the current technology, it has miniaturized. Like dynamic, we have distribution. This thing, what do you call it, bar compensators, like that. Statcom, distribution statcoms. We have distribution statcoms now, which is very portable nowadays. Likewise, this has also become very portable, and it can be mounted on the line, or on the substation, or on as a mobile and a mobile carrier tractor. Okay, as it can be deployed wherever it is required. It is a single phase unit. You have to provide 3 numbers for the 3-phase system. It can act either in a push mode or pull mode. Okay, push mode means it will push the power from one circuit to the other. In pull mode, it will pull the power from one circuit from other circuits to the particular circuit of interest. It's like that. I can show you the picture. Let me see what it is. Now this is the okay. So actually, you can see this. This is the device. You can see the device now. This is the device.
Yes.
It's basically a static synchronous series compensator. Single phase modular static synchronous series compensator.
Okay.
It along with the software will determine how much power has to be. I mean, basically load for algorithm. Basically, it takes information from the SCADA system and then do the analytics.
Okay. Nice. Even power savings also can be done with that, no?
Exactly. If you remove the overloading, there will be loss reduction. You can optimize the dispatch basically.
That load can be, I mean, losses can be saved.
Losses can be saved. Not only that, you can optimize the dispatch. So from a longer route to a shorter route, those things can be done. It is. I mean, it is now. It is in India. It is brought up by Sterlite. They are the innovators for this. They tried to in a case they came out to KSEB to do a pilot, but at the time we couldn't do it.
Yeah. Friends, Engineer Biju is one of the very good faculty members of KSEB Limited. I'm requesting you to make use of this platform and you ask your doubts. He is a senior member and member of PES too.
So I guess there are no further questions from the participant side. Thank you so much, sir, for this wonderful session.
Yeah, thank you.
So
That's
before we conclude this session, let's take a virtual photograph to capture this moment. I'd like to request all of you to turn your cameras on and bring a smile to your face. And I'd like to invite Mr. Anandakrishnan to click the picture. Thank you so much, Anandakrishnan. As a token of appreciation from our side, we would like to present Biju sir with a virtual memento. For that, I would like to invite Anandakrishnan to share the screen and present the scene.
Yeah, thank you.
Okay, so now let's move on to the vote of thanks. For that, I'd like to welcome Ms. Dia Jose, the content writer of our student leadership team. Also, the feedback form will be shared in the chat box after the vote of thanks. The certificate will be distributed based on it. So kindly remember to fill it out. Now, I'd like to invite Dia Jose.
Hello everyone. At the center of this digital transformation, organizations are looking to move away from the legacy enterprise IT systems that required long development and upgrade cycles. And this is why IEEE Education Society Kerala chapter has organized this talk session powering the future on the topic innovative assets management and maintenance technology in power systems. So, on behalf of all the IEEE EDSOC Kerala chapter volunteers and members, I would like to express a sincere gratitude towards Engineer Biju S.S, Executive Engineer, KSEB Limited, Relay Division, Trivandrum, for accepting our invitation and enlightening us with your experience. Thank you, sir.
Thank you.
Now, I would like to thank the main pillar of the event head, Ms. Neha S, for coordinating the event from start to finish so beautifully, and also to all the volunteers who worked behind this event to make this possible. I would like to thank all our participants for your time and cooperation. You are our strength, you are our everything, and we hope to see your active participation in our upcoming events as well. So, thank you all and have a nice day.
Thank you so much, Thea. I would once again like to remind the participants to check the chat box and fill out the uh, feedback form. And I'd also take this opportunity to thank our speaker once again. With this, we have come to the end of our session. I really hope that you all had a great time. Once again, thank you all for actively participating in this event and making it a great success. We'll be back with new and exciting events and talk sessions soon, and we hope to see you there also. Thank you and have a good night.